Let us see how to write the Verilog code of SR flip-flop using positive edge trigger. This is a logic diagram of SR flip-flop which is drawn by using NAND based latch. So from here to here, this is called as NAND latch, and the starting stage is driver, which is used to drive this particular NAND latch. Inputs here are S, R and clock. Outputs are nothing but Q and Q bar. Now for this particular thing, we shall write the Verilog code. In order to write the Verilog code, you need to know the truth table of SR flip-flop. So here I have written the truth table of SR flip-flop. When input is 0, 0, it is nothing but Qn, which is memory. For 0, 1, it is 0. For 1, 0, it is 1. And for 1 and 1, it is don't care. The same thing we need to indicate while writing the Verilog code in behavioral style of modeling. So if you see this particular block diagram, inputs are S, R and clock. Outputs are nothing but Q and Q bar. So let us try to write the Verilog code, which is source code first. So everything starts with a module. So module, this is nothing but the module name that I am taking. You can take any other name also. Module name. Next comes port list. So port list is nothing but outputs and inputs. So I am taking Q, which is output, S, R and clock as the inputs. So as of now, I am ignoring this particular Q bar. If you want, you can write the code by using Q bar also. Next, output register Q is 1 tick B0. So this is nothing but port list. Among this, Q is nothing but an output, and I have taken here as REG. Why? Because in behavioral style of modeling, output should be indicated by means of register. And you may get it out like why I am taking Q is equal to 1 tick B0. So as this is a memory, flip-flop is nothing but memory which holds some previous state. So in order to indicate that, I have given some previous value which is 1 tick B0. Next, this S, R and clock are nothing but input. So you have to write as input, S, R and clock. Next, I am writing the code by means of behavioral style of modeling. So always at the rate positive edge of the clock. So pos edge is nothing but positive edge of the clock. At the rate is nothing but an event. Always at the rate positive edge of the clock. I am writing the code by means of case statement. Case S comma R. So here this indicates concatenation operator which is used to group multiple variables. So case SR are the two variables. For two variables, 4 combinations we get, that is 0, 0, 0, 1, 1, 0 and 1, 1. We have to write it something like this. It is 2 tick B0, 0, 2 tick B0, 1, 2 tick B10, 2 tick B11. Here 2 indicates size, B indicates the format. Colon. So in the truth table we have already seen for 0, 0 I am getting output as memory. So that's the reason I am taking as Q. For 0, 1 we are getting output as 0. So that's the reason I have written here as 1 tick B0. For 1, 0 I am getting output as 1. So that's the reason it is 1 tick B1. And for 1, 1 we are getting don't care. If you want, you can write here as don't care or else Z, which is high impedance. Either you can write as 1 tick BX or else 1 tick BZ. Anything is fine. X is nothing but unknown. Z is nothing but high impedance. And whenever there is a case, there should be end case. Whenever there is a module, there should be end module. And here you don't know this less than or equal to operator. Generally this is called as non-blocking assignment. Whereas equal to indicates blocking. Equal to means blocking, less than or equal to means non-blocking. Non-blocking is something which is parallel in nature. Blocking is something which is serial in nature. So this is the source code of SR flip-flop using positive edge trigger. Next, let us write the test bench also. So next, test bench module, some name. For better understanding, I have taken here as TB. And one more important point, every line should end with a semicolon. In test bench, inputs are treated as registers. So that's the reason all the inputs which are S, R and clock are treated as register. Outputs are treated as wires. You need to remember these points. Inputs are treated as registers. Outputs are treated as wires. Next comes instantiation. Instantiation is nothing but simply calling the particular module for which I am writing the test bench. So name followed by the instance name. So I am calling this particular SR positive edge trigger. This name and the source code name should be same. So let me show you this one. These two names should match. SR underscore pos edge trigger. By means of this name only we have to call it in test bench. So the same name followed by some name, instance name UUT, and outputs are Q, S, R and clock. This is nothing but ANSI style of declaring. If you want, I'll show you the another method also in order to instantiate this particular code. So we are done with module some name. Inputs are treated as registers, outputs are treated as wires. Done with instantiation part. Next, initial, begin. Whenever there is begin, there should be end, and we have to initialize some values. So S is 0, R is 0, clock is 0. So here I am taking some dollar monitor statement and some dollar time. So why I am taking this particular thing is in order to indicate the result in console window, I am adding this particular statement. If you want, you can add it, or else you can ignore this one. So dollar monitor, dollar time. So the same variables will be there again. Output Q is percentile B, where B indicates binary. Similarly S, R and clock. And this is something which is format. Q, S, R and clock. This line is completely optional. Only if you want to see the result in console window, you need to add this particular line. And outside this initial block, we have to write always. So always, for every 5 nanoseconds of delay, clock is complement of clock. So it should get toggled automatically, something like this. For every 5 nanoseconds of delay, it should get changed, and it is positive edge trigger. So going from 0 to 1. Similarly, I am applying inputs for S and R also by means of always statement. So always, for every 20 nanoseconds of delay, S is S plus 1. Always, for every 10 nanoseconds of delay, R is R plus 1. So automatically it will keep on applying inputs, that is 0, 0, 0, 1, 1, 0 and 1, 1. And whenever there is a module, there should be end module. So this is a way of writing test bench. So in the upcoming videos, I'll try to execute this particular source code and test bench using Xilinx ISC Design Suite 14.7. Thank you.